long as it doesn't oversteer. Oh, I don't know yet. I probably won't need it much, so in case I'll wipe it later, or I can probably just use this. Sorry, for whatever reason, it doesn't actually display this thing here. Just don't. Good. Yeah, this is just the camera being too smart for its own good. If I do this, it gets brighter. Okay. So, welcome everybody. Yeah, apologies that last week neither Suvrit nor I were around, but we were both traveling. This was partially. Are we recording? Okay. This was partially due to the fact that, well, basically it's open house this week, so I hope you had a good opportunity also to talk to all the prospective PhD students and convince them that the weather in Pittsburgh is beautiful. Yeah. And so basically I was supposed to be away this week, and Suvrit, yeah, and teaching last week. So this is, I want to apologize for this. Okay, fine. Now, let me continue with the count-min sketch. And what we're going to do today and on Wednesday is we'll cover the count-min sketch, then we'll move on to basically applications of this, and in particular hash kernels, and also matrix factorization, so coffee rank. So this will probably cover most of this lecture. Next lecture, we'll look at a different application of the count sketch, which is almost like the count-min sketch, and I'll show you the differences between the two in passing because they're almost identical. quite unsurprisingly, they both were written at Rutgers in the same department, but by different groups of authors. And then basically in the context of matrix multiplication, and we'll extend a result of Pach a little bit. So this is actually new stuff, but it's probably not big enough to warrant writing a paper about it. But it's kind of nice to have as a diff on that paper. Okay, good. Kant-Min sketch, well, just a brief recap because we already covered that anyway. And by the way, if you have any questions, do not hesitate to ask. And I'm seeing we are now down to about 20 people. So you can next time just move further up to the front, right? So Kant-Min sketch, basically the idea was for an insert, you would increment the counters for all the locations where you hit it with a hash function, right? So if I want to insert x into the data structure, then for each row I compute a different hash function, hash I of x, and at that location, I increment the counter. Quite obviously, this would be very stupid if I didn't have a different subscript I, because otherwise I would be incrementing the same column in every row, and all the rows would be identical, so that wouldn't be a very smart thing to do. And actually, for the analysis, all I need is that I have two-way independent hash functions. So that's about as weak as it gets. Now, what I then do is for a query, since I know that these numbers only could have gotten incremented whenever I performed an insert, and that could have happened only if I saw that key or if I saw something else, each of those counts is going to be an upper bound. And so taking the minimum will still be an upper bound, and that was basically the analysis. And of course, you can increment and decrement, and as long as at the end of the day, the total count is greater or equal than 0, everything is good. So jokes of the form of 9 people entering the elevator, coming out on the top floor, 10 people walk out, the mathematician is surprised, he decides to walk back in and disappears. That will work with a Kant-Min sketch, right? If you had numbers of arbitrary signs, this wouldn't work anymore. So rather than taking the min, you would actually have to take the median. And this is called a count sketch. And the big difference there would actually be that rather than these inserts, let me actually write them out because it's almost identical, you would multiply them with a Rademacher hash. So let's just write count min. So this is basically core mode and Muthu Krishnan. And so the idea there is you increment m of I and hash sub I of x plus equals 1. Okay. And then for all I. And then this is insert, and query is the minimum of overall i's of m of I hash sub I of x. Right. Now, for the count sketch, so this is Charikar, Chen, and Farrah Colton. And I think it's around 2003, if I remember correctly. This operation gets changed by multiplying with sigma sub I of x and replacing this by a median times sigma sub I of x. That's the entire difference between those two algorithms. Okay, so now let me explain what's going on here. The sigma I sub I of x is a Rademacher hash. which has with equal probability values plus, minus 1. And furthermore, you have that expectation over sigma I of x times sigma I of x prime equals 0, and likewise there as well, also for i's and j's. So basically, this holds unless I equals j and x equals x prime. In which case, the expectation is what? What's the expectation of this if I equals j and x equals x prime? Exactly. Yeah. This is just a sanity check to make sure that everybody's still awake. Thanks. Okay. So now, what is the difference between those two things? Well, if I use the multiplication with the random 1 or minus 1, then I can see that in expectation, the value of m of I hash of I of x times sigma I of x is going to be just whatever value of x that I had before. Because what we have is that m I and hash I of x is basically sigma I of x times n sub x plus the sum over all the cases where x prime is not equal to x of sigma I of x prime n x prime. And since this occurs with equal probability, it follows that in expectation this term here is 0, and so everything's good. So now the difference is that for the count-min sketch, we will get a rate, and this is what we already showed, right? This is basically the thing that we went through. We'll get a rate of 1 over epsilon. So number of storage bins goes like 1 over the accuracy. This is great news. Basically, I want to have it twice as accurate. I use twice as much storage. For the count sketch, this doesn't hold. So for the count sketch, I actually get an order 1 over square root n rate. So basically, for the count min, I get epsilon goes like 1 over m. And for the count sketch, epsilon goes like 1 over square root m. Of course, orders. Right. And this is also the reason why the count min sketch was such a huge deal when it came out, right? Because this was actually the first non-trivial sketch that would give you the 1 over number of bins rate with very well-behaved constants. Okay. Any questions so far? And yeah, by the way, this 1 over square root m rate you get basically by first working out what the variance is, and well, which is very easy, and then just use the median mean theorem, except that we don't really use any means. So it's just, well, if I take the median and if I know what the range is, then I can automatically argue that, having more than half the observations outside that a suitably chosen range is hardly ever going to happen. So it's basically just the same idea as before. Okay. Yep.
So in practice, count-min sketch is much better.
Count-min sketch is way better if you have non-negative entries. If you have negative entries, you can't use it. That's a big bummer. Because if you have negative entries, then you can get cancellations. So let's say, for instance, x is 3 and x prime is minus 2. Then if they collide, they will get the value of 1. And that, of course, is less than both x and x prime. And so I have a problem. So this is why you actually need non-negativity quite strongly. Yep?
Can you just explain a little more what you meant by that? So, in your example of 3 and minus 2, is that the function that we're calculating the hash of?
Okay, so basically, let's say x and x prime collide.
Sure.
And x, so, I basically insert x 3 times, and I withdraw x prime twice. So basically, I have a negative value. In which case, well, basically, the aggregate value between those two is going to be 3 minus 2. And that is a lot worse than, it's wrong. It's not an upper bound anymore. So
you're saying with removal queries, you can't use count negative?
With removal queries, that will make some of the counters negative.
Right. And
if
this works with removal queries also?
Yeah. So basically, the count sketch works with negative entries. The count min sketch can have negative entries at some intermediate point when I am not looking, as long as in the end I get a count that's greater or equal than 0. So the elevator will swallow the mathematician. That's the unfortunate thing. Thanks for asking. Any other questions? So, you remember the analysis, and basically all you do is you just, first of all, work out the expectation. You see that the expectation is quite well behaved, and then you just apply Gauss Markov, and you say, well, per row you're with only, probability 1 over e going to be further away than that. And since you have several rows, failing on all those counts is going to happen only with probability e to the minus d for d rows, and then you're done. So it's a very, very basic elementary proof. It doesn't even require any fancy tail inequalities. It's one of those things that, a talented undergrad could easily work this out. And you just get upset at yourself for not having seen this. It's just so beautiful. Okay, good. So now, one thing that you can do is, sometimes you have range queries. And if you actually, let's say, for instance, I have IP numbers. Then I have 2 to the 32 possibly different locations that I need to store this stuff. Now, if I do this, this is actually very costly to retrieve all the numbers. Because if I say have, a class A subnet, then retrieving all the numbers for this class A subnet is actually very computationally demanding. So an easier way to address this is by actually storing the top counters here explicitly, and then only dealing with the incremental counters on the leaves. So this way, you make absolutely no error here. And also what you're then dealing with at the leaves has a smaller cardinality, because you've already caught most things here. And then you just deal with it in the end. So that's something that you can, for instance, do to get higher accuracy and also make it faster. So at some point, AT&T actually had that running to monitor how much people use their phones and so on. So this was actually part of then a larger engine which had a SQL server inside. Likewise, for range queries, you only need a couple of nodes as you traverse down to get that range. And so basically, you only end up querying a logarithmic number of nodes for that range. And so you get high accuracy as well. So the Kormod Muthukrishnan paper actually has a fair amount of detail in that. The thing that's quite important for us are Zipf-ian distributions. So anybody who's done any natural language processing would know what you get there, because you basically only have a very small number of very heavy hitters, and everything else is just very tiny. Now, our sketch has a similar property to those heavy tolerant sketches that like Space Saver, right? Basically, if I have some large number that's very much localized in one bin, then chances that this number will foul up anything else but its own counter are tiny. Because I would have to get unlucky, each and every time. So therefore, what happens is that those sketches will actually work very well for distributions where you have a faster decay of the counts. As a matter of fact, if you just work out, what the count is after ignoring the heaviest items, well, you basically get a guarantee that is, well, okay, here's the entire analysis, but basically you get some space that now goes with, let's say, for instance, z equals 2, then we have 1/2. So it goes like epsilon to the minus 1/2. In other words, epsilon goes like 1 over storage space squared. So it's actually kind of good news. And the way how you analyze it is you basically look at your bins in your count min sketch. And then you basically ask the question, which bins are going to be heavy? And let's say we designate 1/3 of all bins as heavy. Yeah, I guess you can also color it in your mind, whatever. And so only if I end up hitting any of those bins, that's a large number. But for the rest, the count min sketch now works with a tighter guarantee. Because I am, in this case, not hitting one of the heavy bins. And so since I have then a tighter guarantee, which, because I now know that the residual tail is very small, because I have the Zipf's law distribution, that's basically all you do. Right? So that's basically the expected value if I don't have a heavy bin is, the actual count plus then I need to overweight because, we're only taking 2/3 of the bins. Here's the sum going from k equals k plus 1 up to infinity. That's basically the tail that we're cutting off. And then you just work out what that sum is, and that's easy. Yeah. So it's not a big deal. Any questions? Everybody's very quiet. Is everything so clear? Is the homework boring?
The tree part was not clear.
The tree part.
Yeah, like you say you do the track and do exactly.
Okay, so basically what you can do is you can, at the higher level in the data structure, you can just exactly keep track of how many elements you've seen. So you basically use your sketch only for the final resolution. So for the first 16-bit, right, we only need 2 to the 16 different counters. So that's basically 60,000 counters. Well, 65,000 something. But that's not a lot of memory that you need to store. So that may be only, 256 kilobytes of memory. So you can actually store those counters exactly. And then you only need to worry about within that structure where the heavy guys are. So that's the idea. Okay, so because then you get that part exactly, you sketch the rest, and you only need to worry about getting the numbers for the rest. So this has 2 advantages. First of all, you store exactly where the big guys are, and then for the rest, you just don't worry. Okay. Now, here's a really nifty idea of how to extend this, and this is a paper due to Montanari and co-workers. It's called the counter braid. And as beautiful and simple as the algorithm is, the proof is a little bit, let's say, unsatisfactory, partially because it refers to a book that never was written for the main idea of the proof. Given that this is Montanari, you can assume that the proof probably goes through. Yeah, okay. So here's the idea. So for the counter, actually, it's standard count min sketch. And we have an a priori lower bound of each counter of being 0, right? So what we can do with this is, well, we can basically get an upper bound for each of the counts. Right? And now, what you can do is you can basically look at any of those matrix elements. Okay, I call them Wij here. I should have actually called them Mij, but anyway. I know that the elements in bin Wij are just the sum over all the keys for which hash of I and key equals j. So these are exactly the collisions, right? So that's the total count. Okay. Now, I also know that this is less equal than, well, Cx, where Cx is basically a number that I get from, some upper bound that I had before. So suppose that I have Cx as an upper bound for each of the counters. Initially, that one's going to be infinity. But what I can do is I can obviously write that Cx is greater or equal than a new lower bound, which is basically Wij minus the sum over all the upper bounds for all terms except x that I'm interested in. So initially, this result is useless, right? Because if all the Cx's initially are, infinity, then, well, something finite minus infinity is going to be, minus infinity. So that lower bound isn't particularly good. But what I simply do is I take as my new lower bound the maximum of the old lower bound and the new lower bound. So if I initialize that with lower bound being 0, it doesn't really change anything. So what I should actually do is I should start the algorithm with with getting this upper bound, which initially is infinity. So I, of course, know if I have a lower bound for each of those counts that it's greater or equal than, well, the sum over all the lower bounds. And so therefore, I have that, a new upper bound is going to be Wij minus the sum over the lower bounds. Okay. So this gives me an upper bound on the count. So in the first stage, it's just a count min algorithm. Now, once I have this upper bound, I can get a possibly tighter lower bound. When I have this tighter lower bound, I can go and work out a new tighter upper bound. So you're basically ratcheting the constraints from above and below. Initially, the constraints are, well, I know that they are non-negative numbers, and I know that, they are bounded by infinity. And so you go and tighten things up. Once you've done this once, you keep on repeating it. And the nice proof in the counter Braids algorithm is that you can basically show that under reasonable conditions, this algorithm will converge to the true answer. Okay. Can somebody see the Achilles heel in this approach? What do I need to know in order to run this algorithm? I need the count min sketch, data structure, and I need something else. What is it? Exactly. So you need to know the domain. And in many cases, it's a non-starter. There are a couple of special cases where it works. So for instance, if you're running this algorithm on a network switch, and it's an IPv4 network, I know that there are only 2 to the 32 different values. So as long as I actually go through all of them, I can do it. This sounds insane, right? It's 4 billion numbers. Actually, it's not that insane given how fast computers are and given how cheap maybe network switches are. So it's not completely ridiculously insane. It's just borderline crazy. Okay. But this is what basically gives you the tightening upper and lower bounds. And you can use this to, well, get accurate values. Okay. This very same idea, just in one iteration, and they didn't actually realize what they had, was something that people used to date Twitter activity, right? So because when you crawl Twitter, Twitter will not tell you when somebody signed up and when somebody followed somebody on Twitter. However, what you do have is a chronological order of when the tweets were, when people started following. Okay. So let's say here's user 1, and here's user 2, and here in between is Justin Bieber. Okay. It matters that you pick somebody like Justin Bieber. User 1, the first thing he does, or maybe the second thing he does is, oh, well, let's follow Justin Bieber because everybody does. Okay. And then user 2 decides, well, yeah, Justin Bieber is great, but maybe not as great as Lady Gaga, but let me also follow him. Okay. Now, what also happens is that maybe I also follow Justin Bieber. Well, no, don't worry, I don't. But, okay. Okay, so I also follow Justin Bieber. And by the way, I decided to tweet here. Right. So now I know that my following activity must have happened before the tweet. Furthermore, I cannot have started following Justin Bieber before I even created an account. So therefore, you basically have useful constraints. You have the constraint that you can't follow somebody before you even created an account. And secondly, well, the tweets give you relative timestamps. Furthermore, the following relationship that you get from Twitter is reported in order. So if basically this user at some point decided to also follow Lady Gaga, and I query, who user 1 follows, it will report something like, okay, and let's say he is also interested in machine learning. Would be kind of a weird person, but anyway, so the follower relationship would be JB, LG, and then Alex. Yeah. Okay, good. So while that doesn't tell you when I followed, it tells me the relative temporal order. Now, by having a lot of those relative temporal orders, you get upper and lower bounds for following. Because I cannot follow you before you've actually created an account. Right? And I cannot be followed before that time either. Furthermore, I need to have created an account when I tweet, before I tweet. So what they did then is they used this basically for lower bounds. But what they actually should have done is iterated these conditions to get much tighter guarantees. But that's not a paper in its own right. So you could probably do it for something else that's really useful in this context. But anyway. Okay, so what I'm trying to say is those tightening inequality tricks you can use in more than one context. And here are two contexts, namely Justin Bieber and then also counter braids. And yeah, okay, so if you wonder why Justin Bieber, a couple of years ago, apparently 3% of all servers at Twitter were just being used for dealing with Justin Bieber. My guess is that number would have gone up in the meantime. Okay. Anyway, so while this is useful when I know the domain, it's still quite wasteful. Sorry, there's a question. Right? Was there a question somewhere? Okay. So the wastefulness in this approach is the following. If I don't overload my count min sketch too much, a lot of the entries will be 0. And now here comes the really ingenious part. To go and not store the full 32 bits per counter, but use only, let's say, 7 bits, and then use the last as an overflow bit to indicate whether I insert it into the next count min sketch. So basically, whenever you overflow, you reset from 0, and you insert into a new count min sketch, which is now smaller. So you now get the logarithmic encoding, right? And since we know how counter braids work, all I need to be able to do is just peel off that very last bit to infer how many overflows I would have had at the previous level. I then use the same algorithm again to infer how many overflows I would have had at the next level. And in combination, I can therefore then design a sketch which is actually fairly space efficient because it doesn't use too many bits at the lowest level and is also with high probability accurate. The only thing is reconstruction is a royal pain. Insertion is very cheap though. So that's why I'm not super fond of that sketch in its own right, but it's a shame that nobody's figured out how to make this algorithm useful in machine learning. Any questions so far?
When do you overflow?
Okay, so let's say I take an 8-bit counter and I observe 10,000 events. Then each time I, cross 2 to the 8, I restart counting from 0, and I will send one overflow message here. Now, this data structure at some point, each of those counters at some point might also overflow, and I send the next signal here. And so then, in order to get, let's say we have 8-bit here and 8-bit there, to get a 16-bit resolution for this table, I first need to solve counter braids relative to here. And then, in order to get, a 24-bit resolution, I'd have to solve, this data structure relative to this. And of course, it starts breaking down as soon as you miss even just one. So you need to have fairly good guarantees, at least at the highest level. Okay. Any questions so far? Okay, good. Then let's move on. So now you can ask yourself, what am I going to do with this, right? So, for instance, how do you scale those sketches beyond single machines? You have limited accuracy, reliability. I want to actually insert more data, and I want to compress things. So the 3 tools that I'm going to use is count min as before, then consistent hashing, and then actually I'm going to use interpolation. So I'm basically going to use statistical tools to make up for the fact that I've thrown some data away. So who knows consistent hashing? Okay. 2 hands go up. 3. Any more? Okay, good. Well, not good, but this is actually an awesome thing that's really worthwhile knowing. And you've probably used it. Who has done balls in bins type of analysis in theoretical computer science introduction? Nobody else took a TCS class? Shame on you guys, you need to take one. This is good stuff. Okay, so here's basically what we have. We have a huge data stream coming into a single machine, and that machine will get overwhelmed. So what I want to do instead is I want to be able to partition it uniformly over a bunch of servers. And so what I'm going to do, so don't do this at home, there are smarter ways of doing this. Talk to Zishao or Mu or Junwu or anybody else. But what you can do is basically you would take the argmin of the hash of the key and the machine ID, and I will then go and pick the machine with the smallest hash value. Okay. So this is similar to picking a random element from a stream. The idea goes back to Karger, to his old Akamai paper, which is a beautiful paper for the algorithm, and the algorithm's on the first 2 pages, and then there's a tour de force of 8 pages of proof. And my guess is he would have had more impact and popularity with this algorithm if he'd put that into 2 separate papers, because all the programmers got scared of the math and put the paper back into the stack. Yeah. So I'm trying to solve the following problem. I have a machine pool of 1,000 machines, and I want to send keys to this machine pool in such a way that next time I see the same key, it goes back to the same machine. And furthermore, that I have essentially uniform load balancing. And furthermore, I would also be able to have a setting where I don't lose too much performance if I need to rebalance things later on. So for instance, let's say I am running one gigantic web page cache, because maybe the network cost for CMU is too high because people watch a lot of YouTube videos. And so what I at some point realize is I'm actually running out of space on a single machine. So I'm going to purchase several caching proxies, but I want to make sure that the same file gets requested from the same machine over and over again. There are some issues with what I just described, because you have actually fairly uneven loads, because I guess Gangnam Style gets watched a lot and maybe my videos a lot less. So you need to have another special mechanism for dealing with this. There's actually a beautiful paper that you can read, preferably after a beer or 2, or maybe wine. It's very slow, very detailed, but it's a nice paper. They got a best paper prize for it. It's called SPOCA. It's, I think, stateful. No, sorry, stateless. Sorry about that. Yeah, big difference. Proportional. Consistent hash caching. And it actually solves the problem of video distribution for Yahoo servers in this case. One of the authors would be Ben Reed. It's a very nice paper worth reading. And it's easy reading. Okay. Anyway, so let's for the moment assume that the loads are even, otherwise you need this. Okay, good. So if I do this, then I can immediately see that uniformly over all the machines, I will get the uniform distribution of keys of a machine. So because the probability for a key to be assigned to a particular machine is 1 over size of the machine pool, because I have this hash function. Okay. It's reproducible, which is nice. So next time the same request comes along, it goes to the same machine. So I don't need any central mechanism to decide what goes where. Mind you, in the old days, how people used to set up, yeah, that's this paper, Usenix 2011. Mind you, how systems used to be set up in the old times is you would basically do some provisioning, and as more users came along, you would add more machines. And one of the obvious downsides is that you would have all the recent users on one set of machines and all the old users that may have gone away on another machine, and maintaining that entire index mapping was a total nightmare. This way there is none. Well, the problem is, though, that you actually may want to rebalance things. So if I do this, first of all, I can actually increase my throughput a lot, right? Because I have more machines, so I can do more inserts per second. So the throughput increases with order number of servers. Furthermore, the accuracy, if I run count min in this way, and because that might be the first thing that I might want to do, is it actually goes like 1 over number of servers, because more servers means more memory. And since now each key is only contained on one machine, well, I basically have k times as much memory available. This is all good news. The unfortunate bad news is that the reliability goes to hell. Because as soon as I lose just a single machine, will I not be able to decode an entire subset of keys anymore. Okay, so this is bad. So how can we fix this? Well, one way to fix it is actually very trivial, right? So you look at the count min sketch data structure. I have several rows, and I put each of those rows onto a different machine. Okay, sounds great, right? The good thing is my failure probability decreases exponentially. This is good news. Because now, before a disaster happens, all the machines that have this key have to die. Here's the bad news. Well, the throughput is constant because each machine now needs to process each of the keys. So, in other words, having more machines doesn't do anything to making my system go faster at all. Well, it makes it a little bit faster, but the dominant factor is really the network, so it's really bad. What is horrific is that the query latency increases. Because now, in order to actually ask how many times did I see a particular key, I need to ask all the machines, and I need to wait for the last machine to come back. And if you remember, this is really, really bad, right? Because what we had is, if I have the max of a bunch of random variables, I going from 1 to k, the cumulative distribution function of that was the original one, f naught raised to the power of k. So in other words, with a very high probability, will I get very unlucky and end up with one machine that is much slower than it should be? Okay. So this is bad because, well, it's not fast. So there's obviously a solution to doing those two things. Well, very simply, you do a little bit of both. You basically have a single machine, but now instead of inserting into all the servers, you only insert into a subset of the servers. And then when you query, you only need to query a subset of the machines. And as long as I get the subset partitioning sorted out in a random uniform way, everything's good. So here's the math. So you assign the keys only to a subset of the machines, and you over-replicate a little bit for reliability. You also over-replicate for query parallelism, and now, so remember before that when we used consistent hashing, I said, well, pick the machine for which this hash is the smallest. Now we are going to use the same trick as with shingles. I'm going to pick the k machines with the smallest hash. So this way I can uniformly distribute over subsets of k that have a uniform distribution over all the machines. If I wanted to have different loads, then there are interesting things you can do with a hash function and so on. So that's not very hard, actually. So for instance, you could multiply each of the capacities with a number like 1 over the load, and then you can do interesting things there. But now, as long as you request from a sufficiently large number of machines, and you basically don't have to ask all the machines, so you don't wait until all the machines return, you're done. You basically overdo it slightly such that if you lose a machine, you still have good accuracy. And so then you can do the following. You basically go into the count min sketch theorem, and you modify the proof a little bit, and what you get is that if I have f failures among m machines, and I assume that the number of requests that I have is less than half the number of machines, then, and if you you can kind of sort of see it, you need 1.7 less than 1.72 times number of failures times number of rows divided by number of machines, additional inserts over the single machine count sketch for this error. And that's usually a very small number. As your machine pool might be in the order of maybe 100, failures might be maybe 2 or 3. And, well, this is maybe 5. So this is 10 over 100. So basically, it's like, in practice, 1 extra insert is good enough. D is the number of rows in the count-min sketch. So this is, right, it's that. So you basically need 1 extra machine in practice to deal with this fact. Now, the thing that you exploit in the analysis is that the count-min sketch itself may fail with a certain probability. So by over-provisioning, you're getting slightly more back from the over-provisioning by having more machines than what you end up paying by, being unlucky and losing 1 or 2 rows. And so once you go into the analysis, you can see this. Yeah, it's fairly straightforward. So basically, so the key trick, otherwise you end up spending a lot of time, is you majorize the drawing without replacement by drawing with replacement. Basically, yeah, that's really the only issue, because if I have F failures, well, I could get, well, I mean, basically, the machine that's failed cannot fail again. But the thing is that if the number of failing machines is less than half, then this inequality works the right way. This is why you have that condition up here. So basically, it's worse for you if you fail with replacement in this case. Otherwise, you wouldn't. Okay, so basically, what you get is this very simple strategy. So this is an example of, data analysis combined with randomization. And you actually have 2 different types of, randomization here. You have one on the system side, which, decides to which server or equivalent to, row in a matrix the data goes. And then you have a random subset for your query. And if you want to do load balancing, you can have another level of consistent hashing here. You might have noticed already that consistent hashing, the way I described, is super expensive, right? Because if I have 1,000 machines, I need to compute 1,000 hashes. I need to find the smallest entry from that, or the k-smallest entries, which is, a problem. What you can do instead is you basically use a distributed hash table, and then you can reduce it from order number of machines to order log number of machines, because you just need to do a lookup. You lose a little bit in terms of evenness of balancing, but that would be a systems class. If you take that, they'll probably teach that. Okay, but you basically have those 2 effects. You have the statistical guarantees, and you have the reliability guarantees from the algorithm and from the system side, and those 2 actually, nicely match. So the big benefit over just dumb replication is that by having more machines, not only do you gain reliability, but you also gain accuracy. The open question is how you can actually do self-repair there. And I would dearly like to know how this could be done efficiently. So if you have any idea, I'd much appreciate it. So let's say I lose a machine. So I lose some of the rows. Now, if I keep on going, at some point, well, I will have lost a critical number of rows, and so the entire system will go down. That's not a big deal if the data is ephemeral and I end up throwing the data away faster than I would typically lose machines. But what I would like to do ideally is that after a short term, I can basically rebuild my index in such a way that I can then lose another D machines. So this is to some extent possible with checksums and so on. So basic error correcting codes will help you address some of this, where then you need to do more than one insert, but it's not very pretty. So if somebody has an idea for something prettier, it would be great. Okay. Any other questions? Okay, good. So then let's move on to something where we can use machine learning a little bit more directly, interpolation. So remember the count-min sketch? Well, and the count sketch would actually have the same properties. It's, well, you know, that a sketch of two sets is the sum of the sketches. So the goal here is I have a data stream that comes in, and I might want to be able to answer a question like, how many users did I see yesterday? Or how many users did I see yesterday at 12:14 a.m., right? And how many of those users searched for Justin Bieber, right? Okay. So, yeah, given that this is all going to be video recorded, it will be amazingly embarrassing in 5 or 10 years when Justin Bieber is not cool anymore. Anyway, so basically what you want to be able to do is have time intervals and also get items. And so the dumbest thing that you could do is basically buy a really fast disk or an SSD. And you just, you know, build a sketch for 1 minute, you compress it, you dump it to disk, next sketch disk, and so on. And you keep on doing this. At some point, you run out of disk space and you buy a new disk. This is still better than what a lot of others do. But actually, if you think about it, this is doing a lot more than what you care about. Because for old data, you often don't care about the accuracy quite that much anymore. So the question is, maybe we can interpolate. And also, you know, can we compress those things fairly efficiently? So the first thing is to realize that if I have longer and longer time series, so let's assume I just care about storing a sketch where the time intervals, you know, increase exponentially. So what I get is basically that adjacent intervals give me the next power of 2. So 1 plus 1 is 2, 1 plus 1 plus 2 is 4, and so on. So this cumulative sum can be seen to be, can be engineered to be powers of 2. So what I therefore get is that 2 intervals of length 1 will give me an interval of length 2. 2 intervals of length 1 plus 1 of length 2 will give me 1 of length 4, and I can just work out those cumulative sums for larger and larger powers of 2. So the algorithm therefore works as follows. So always go and fill the first bin. So what I'm now doing is I'm basically going to keep, for a time interval of length t, I'm going to keep t bins around, log t bins around. Actually, this is wrong. It's order 1 amortized. After I made those slides 2 years ago, well, we figured out that it's order 1. It's actually a very simple proof. You may have fun with that. You might have fun with that proof. But storage is order log t. Okay. Basically, here's what happens. So you always fill the first bin, so you always need to do this work. Every 2 steps, you need to add 2 bins together. Every 4 steps, you will need to add, well, compute 3 cumulative sums. Every 8 steps, 4, and so on and so on. So basically what you end up doing is, with probability 2 to the minus n, you're going to perform order n work. So therefore the sum n equals from 0 or from 1 to infinity of that is a constant. And this shows that amortized work is order 1. The unfortunate thing is that occasionally you have to do a lot of work, but the good thing is that after doing a lot of work, the next a lot of work is going to be a long time away. So as long as I have an aggregation pointer, and I'll show you in a moment what happens, right? So this is what happens here. You can basically spawn off a separate thread which aggregates things, so that's why you will not really be in dire straits. Okay. So initially, this is 1 bin. It gets aged and gets moved over here. We have another bin. Now, okay, so this is how time flows. So this is basically that constant time, but time, data just gets added to the right. And now I have an interval that was the aggregation of those two. I get this one here. Now I go and move this over here. This gets aged. Here we have this. And so now we aggregate those two together. We get the interval of length 4. We aggregate these. We get the interval of length 1. This one stays here. That one gets added. And so I keep on going through. And very unsurprisingly, this is what happens, once I have, intervals of length 8. And so you can see that only very rarely do those large aggregations happen. So think of this like an antenna, like, an old radio antenna that you extend. And you have longer and longer intervals. And occasionally you just squish all together and then you extend it one by one by one by one. And then, the next element comes out again. I mean, that's how I imagine it. And then now here comes the pretty, annotation. This is how you actually store it in memory. So that's how you do things over time, and it gives you, log time storage, and of course you lose a lot of things. So for instance, if I wanted to do this to query logs, then after a year maybe I can only answer the question, how many queries did you see in 2013 about machine learning? Duh, not very useful. There's another thing you could do. So instead of making the time intervals longer, what else can I do to my sketch? Any suggestions?
Reduce the number of beans.
I could reduce the number of bins, number of rows. That's a good point. If I was to do that, I would make the sketch less reliable, right? And I would make it exponentially fast, less reliable. And I might have d equals 3 or 4 only anyway. So that might help me a bit. What do I do after I'm out of rows? What else can I do? What other horrible thing can I do to my sketch? How can I halve its size?
Change the hash functions and
Exactly. Exactly. Perfect. So what you do is you basically just throw one bit of the hash function away. So this right block and this left block collide, and I get this. And I keep it again around. Then after another power of 2 steps, I halve it again. And so again, I get order log t storage and order 1 maximum update cost. So there it's not amortized, it's actually order 1. Okay, so basically what you now do is, and so this is to clearly show what happens, right? So I basically now have 2 sketches. I have one that keeps on getting less and less accurate in terms of my time intervals. I have another sketch that keeps on getting less and less accurate in terms of my item intervals. Both of them operate at order log t. Can I do something with both? Well, it turns out you can. So this was a paper that we had 2 years ago at UAI. You basically effectively have the marginals between a joint distribution whose entries you don't have. This would be, full time. This would be full item resolution. You don't have that. But you basically have at a given resolution level, only the time or only the items. So if those two things were independent, all I would have to do is just look at one entry here, one entry there, look at the product, divide by the total count, and I'm done. This is a maximum entropy estimate in the very simple case where I just have those aggregates, where I'm not making any structural assumptions on how well behaved and temporally smooth things are. If I, for instance, was to know that always on Friday night at 1 a.m. in the morning, the number of searches for adult content goes up, well, then I can probably extrapolate what happened a month ago as well, right? So if I have those additional structural attributes, I can actually learn a regression and do a lot better than just by looking at the product of the marginals. So we're actually trying to figure something nice out there that's computationally efficient. But basically, this trick will give you, in practice, estimates that are almost as good as doing the full thing with only log space. And in a way, this is kind of, it's quite fun because you're really exploiting regularity structure in the data, such as knowing that, well, if the overall search traffic goes down, you know that also the search traffic for a specific thing goes down. Or, you know, that maybe the fraction of certain items is fairly uniform. So those two properties, exploiting them, can help you a lot. Okay. Any questions? Okay. Everybody's very quiet. Have you guys done any sketches before? Was that so? Who thinks this was really hard now? I can turn around and have you count if you want. Who thinks it was really easy? Okay. Who wants to have more of that kind? Or who wants to have more of optimization? Okay. Optimization? Sketches? Okay, that's kind of undecided. Maybe a little bit fewer people for sketches. Okay. We'll go back to more mainstream machine learning topics then. Okay, good. So what I'm going to show you now is hash kernels and linear models. And, well, I haven't really told you yet about locality-sensitive hashing, so this is actually not really a recap, but it's more an advanced preview. Who has heard of locality-sensitive hashing, LSH, before? Okay, good. So, yeah, at least half of the guys here already know what I'm sort of kind of hinting at. So the idea is basically you have this high-dimensional dense vector, and that's kind of awkward to manipulate. I want to have a lower-dimensional dense vector in such a way that any operation that I do with this lower-dimensional dense vector is going to be a good guesstimate for what happened with a high-dimensional vector. Okay, sounds like magic because, you know, I'm throwing dimensions away and it's still okay. And so therefore, of course, those guarantees will only hold with high probability. But in any case, what happens is I take a short and fat matrix, some projection matrix P, and I multiply it with some vector. It's actually tall and skinny, but I would have run out of space in the slide here. And I compute Z equals P times X transposed, if you want like this. Okay. Now, the nice thing is that this operation will, with high probability, approximately preserve distances. Okay. Notice the qualifiers, with high probability, approximately. And we'll be more specific about the with high probability and the approximately part later on in this class. But for the moment, just, you know, remember that. So you can actually try this out on your computer. You have MATLAB generate a Gaussian random matrix. You multiply, you know, short and fat matrix. You multiply a random vector with it. And you look at the distance and the length of this vector, and you'll see that these are preserved if you rescale suitably. Okay. Now, the problem with this approach, sorry?
Is the distribution also, so it's a Gaussian random matrix, right? So is the distribution also preserved?
So it's a good question. So there are different matrices rather than just Gaussian random matrices. So you need certain properties of, I think, stable distribution. So for instance, there's this very nice paper by Dimitris Achlioptas on database-friendly projections, which at the time was a really cool idea, but by now you probably wouldn't do this anymore, where the entries of this matrix here, so rather than having Pij being drawn from a normal distribution with zero mean and, let's say, unit variance, you would have Pij drawn from a distribution where I have values of 1, -1, and 0, with probability 1 over 6, 1 over 6, and 2/3. Okay. And one can show, and that's a little bit more work, but we might just do that actually in the class, that this will still give you a very reasonable projection matrix. And there are some guarantees on how sparse P has to be and so on. So there's a really cool paper by Woodruff and Clarkson from, I think, 2012, where they design an extremely sparse object and still are able to get away with things. But at the end of the day, the problem is that whatever comes out of this operation here is going to be fairly dense. So if I have a dense object that goes in, this is maybe not such a horrible thing. However, if the object initially was not dense, I've just made things worse. On top of that, if I had a very high dimensional object before, then I may actually end up still using even more memory than before. Because let's say I project into a 10,000 dimensional space, this will still require me to spend around 40 kilobytes on this. Right? So that's a floating point number each. And my original document that I would have projected this way might have required less than 40 kilobytes to store. Okay.
I mean, my answer can also, question can also be put it as, is there a distribution preserving hashing, or there is only, you can only do it in distance preserve?
Okay, so there are certain cases where the distribution is essentially preserved. So for instance, Daniel Xu and Sham Kakade have this paper where they take mixtures of Gaussians and they randomly project. And then in this lower dimensional space, it still pretty much behaves like a mixture of Gaussians, as you would imagine. And they actually use this for certain reconstruction properties of the algorithm. But other than that, as I go from a D to a D prime dimensional set of observations, preserving the distribution is kind of a hard question. It's not really well defined.
So it depends upon the metric that you use to compute the...
It's that, but it's also simply, well, the two spaces don't match up, right? So I may have had a distribution over words, so it's discrete counts, and afterwards I have continuous random variables. So obviously, this object has to be a very different object from what I started out with, right? So then you could say, well, maybe something like this might help, but then I still might get negative numbers. So in general, it is a different distribution over attributes. However, in many cases, these attributes themselves can have an interesting distribution property when looking at as a distribution over the projection matrix. Because, I mean, if the entries of the projection matrix are Gaussian, then conditioned on the data, the projections will look Gaussian. So you can do such things, but the more interesting question is basically, how much does it distort? How much will I lose? The practical issue in our case is that if you do this, you throw away way too much data. Because we actually have gigabytes of memory available, so it's not a big deal if our classifier in the end uses 1 billion dimensions, right? That's perfectly okay if I start with maybe 10 to the 15 and I end up with 1 billion dimensions. That's okay. And these are not contrived examples. That's if I, for instance, want to do spam filtering personalized for 100 million users and I have a real vocabulary. So the idea is basically I take my count min data structure and make it even more sparse by only taking one row and then multiplying by a random sign. So here's a more specific example. This is multitask learning for spam filtering. Okay. So let's say I have an email of that form. You can decide whether that's spam or not, right? And Barney gets that email. And so my feature vector in this case would be the tensor product between the user ID and all the token IDs in the document. So if I have 100 million users and I have maybe 100,000 different tokens that could possibly occur, the tensor product is large, at least could potentially be very large. And building a dictionary is kind of awkward, right? Because that dictionary will actually waste a lot of storage because you need to actually be able to recognize each word. So you will need at least 4 to 6 bytes per word if you even just store the hash of the word in the dictionary. right? And then you need to store the key. So you're basically going to pay around 10 to maybe 16 bytes per token. That's expensive. And you still need to do the lookup. So what we did instead is, we basically take a hash function and hash this ridiculously large high-dimensional vector into something that is a little bit less ridiculously large. And now, each entry here gets mapped into only one location. If I have a collision, I just add things up. A small twist is I actually multiply with a random hash, but the obvious observation is the slide is a little bit older. But I just didn't have the heart of updating the email service. Anyway, so here's what you get. You basically multiply this with a random sign of 1 and minus 1. So it's basically the count sketch rather than count min sketch. And it does actually work slightly better if you use the count rather than the count min. We found out empirically, as in we first, so the way how this paper happened is, this idea happened is I saw Muthu Krishnan's talk. I realized, well, this was something really useful for machine learning. We implemented it. Later on, we realized, well, we were actually getting this bias of collisions. So we multiplied with this Rademacher hash. And at that point, this actually worked slightly better. So if you use hash kernels, you should actually use the random signs. OK? And so then, you get those random signs. So that's where you might get the -1 here from there. And maybe those two collide. No, actually, this one doesn't collide yet. It's just mentioned in Barney, goes there. Maybe it collided with something else. And so this now gives you a new feature representation. Here's a couple of advantages. You don't need any dictionaries anymore. So this makes your code ridiculously simple. Just writing the code for the dictionary is actually the harder part of the entire problem, right? Dynamic data structure, what have you, making it all accessible really fast. Or you need to find something, let's say, in Boost. It also means that you don't need to allocate any memory for it. And it also means that you have a finite memory guarantee. You cannot run out of memory because, well, you only have a finite amount of memory available. The other thing is you don't need to store any memory for projection matrices like in LSH. And I have this implicit mapping into some other high-dimensional space, keeps the sparsity. So these are all really nice properties relative to, say, LSH. So let's look at it from the matrix viewpoint, right? So here's that projection matrix. You can see it has only one non-zero entry per column. And let's say 1s and -1s. And multiply with x prime. And this gives me my compressed representation. So the good thing is it really preserves the inner product, like so. At least in expectation here, this is fairly straightforward to see, because in expectation, sigma of I with sigma times sigma of j will only be non-zero if I equals j. So this holds straightforwardly regardless of what I do to the hash bins themselves. The hash bins will reduce the variance, so this is fine. And so this already shows that this is an approximate inner product that with high probability is correct. So in other words, if I have a orthogonality in high dimensional space, then in low dimensional space, well, it's still approximately the same thing. And the guarantees are actually fairly straightforward, namely that if something was orthogonal before, after the projection with high probability, it's still approximately orthogonal. I do not get the canonical distortion measure type of guarantees that LSH has. That's the really unfortunate thing, and that has a lot to do with the fact that they use sparsity. The other nice thing is that when I had orthogonality through direct sums in Hilbert space before, now I just get sums in this hashed space, and things are fairly well behaved. I think we're almost being kicked out, so I just want to show you the results, and then we'll pick it up again on Wednesday. So you can actually prove reasonably decent properties about that. The variance is well behaved. And then it actually works a lot better than doing the unpersonalized spam filtering in this case. So it basically improves things by about a third. This is a small data set, so that's 20 million email, 400,000 users. So it's basically 400,000 different tasks. And the interesting thing was that it actually helped for all users, because if you look at number of labels versus number of users, most users don't label their email. And the surprising thing is this one here, that even for users who don't label their emails at all, it helps. You might wonder two things. First of all, how on earth did we measure it? Secondly, why is this the case? How did we measure it? Well, that's easy. For instance, you can leave out for a particular user the one labeled email and see how well it does there. So that's easy. You can also use additional side information to find out whether an email was spam. But basically leaving it out helps. The other thing is that, well, spammers have email accounts too, and they sometimes have farms of people who spam label certain emails. So what this means is that by catering with a special classifier for the spammers, they will find that their own email spam goes through for their own accounts and nowhere else. So this is the equivalent of a kill file. So once upon a time in news groups, when you had a troll, well, what would you do, right? I mean, you can just disable his account. If you disable his account, that's not so good because, well, he'll just create a new account and come back, right? And he'll aggravate people under the new account. If you block him, likewise. So the idea is not to block him, but to just make sure that nobody else sees his stuff, right? That's what a good collaborative content filtering algorithm does. The hard solution is you simply don't show that user's posts to anybody but himself. So whenever he logs in, he'll see his posts. And otherwise, nobody else sees them. And this way, the spammer, the troll thinks nobody's interested in his things, and he will go away. At least the really stupid trolls. But then, on the other hand, why else would he be trolling? OK, so I want to conclude with that. One thing just to remind you is, I mean, for your projects, you should start about having a midterm write-up soon, right? Because so basically, if you've all forgotten about the projects and are really busy with the midterms and everything, now's the time to think about the project again, to meet and maybe start working on them. And yeah, so I'll be back on Wednesday, and if you have more questions, let's talk then, because I have open house right now and I'll need to run upstairs right away.